theorem we proved last time. So I realized after last class that I forgot to tell you something. So I'm going to say it now. It's about this weird R map, because I've been carrying this around pretending that it's important, and I've never explained why it's important. One reason we've never seen why it's important is because I forgot a part of the proof of that theorem. Because remember, all the time we were assuming that the substructure was a field. And I never explained how do you go from an integral domain to a field. Okay, so if we look at the embedding lemma, what did it say? It said I take M, a model of ACVF, and I take A, actually M and N. I take A inside of M, and I assume to be M plus saturated, and F goes from A into N, and we want to extend it. There is this G from M into N. And what we did is we took a maximal extension of this thing inside of M, and we proved that it was defined everywhere M. But I forgot the very first step, which is to show that the domain is actually a field. Okay, so we took C, we took G from C into N, where C is a subset of M, maximal extending F. And then we proved a bunch of things, but I forgot claim 0, which is that C is a field. Well, K of C is a field. And actually also little k of C, but this is easier. And how do you do that? Well, you do exactly what you think you do. You extend, so you have F, and so what you do, well, on K, you look at K of A, and then you take the fraction field of that. So you localize at 0, and that you can clearly send into N because N is a field. So the fraction field embeds in the field. And little k, you can also localize at 0 and send into, sorry, k of them. And gamma, you don't need to touch because it's already a group. Okay, but so this is obviously a ring morphism because localization is okay. This is obviously a ring morphism. This is obviously a group morphism. But you have to check two things. You have to check that it preserves V and R. And V is clear because it's multiplicative. Okay, so V of A over B is just V of A minus V of B. So there's no question, it's preserved. But R is a problem. Well, no, R is not a problem either because R of A, B, C, D is just R, I'm going to get it wrong probably, but A, D, C, B, I guess. And this is exactly why, yes?
Can you repeat that KA0?
Oh, it's the fraction field. It's the localization at 0. It's just, this is shorter than frac, and I'm lazy. And this is exactly why we put this R, is because now we can compute the residual fractions because it's built in.
What if you just taken res and then completed it to a function any way you want it?
Yes, but that does not work.
Yeah, I know. I mean, what doesn't? What
so I don't want to give the counterexample, but there is a counterexample. So the important remark here is that this seems like a silly problem, but it's actually a fundamental problem. And ACVF does not eliminate quantifiers if you replace R by res. And so there's an explicit counterexample in my notes. But I don't want to give it now. So you really need that weird R, because you really need to know what happens for fractions. Otherwise, things just don't work. It's essentially the same reason that if we were working just in the field sort with just one sort, and if we put the valuation ring, a symbol for the valuation ring, you don't have QE either, because you have essentially the same problem. You need something that talks about division. So you can either put division, which I don't like to do because it's a bit it's a nasty function, or you can put the divisibility predicate, which talks about division. Anyway, so that was first remark, is that this weird R is really, really necessary for the theorem. Good. Perfect. So yes, so that was the first thing I wanted to talk about. So now we've proved a quantifier elimination theorem. So, and last time from it we deduced what are the completions of ACVF. So what I want to do now is try to describe definable sets. So what can we say about definable sets? So the first thing we're going to do is to describe definable sets in K. So not K to some power, but really K1. Okay, so the finite. And to do that, what we're actually going to do is give a complete description of one types of algebraically closed bases. Okay, so let's set up things. M is a model of ACVF. A is a subset is a set of field points such that A is a field and A are. So this is shortcut for saying it's a field and it's equal to its algebraic closure. So it's algebraically closed. Yes, and now we want to describe all types, but before that, what I need to do is I need a small definition. What? Types over A or what? Yes, we're going to describe types over A. But before that, I need a small definition. So if B or F, Fi is 0 to draw, is a pseudo-Cauchy filter, over A, we define the generic of F over A. So that's the generic of F over A to be the partial type. So a priori partial. That says the following. So A realizes eta F over A if and only if for all B ball over A is in B if and only if B is in F. Okay, so A is an accumulation point of the filter, but it's in no smaller ball. Yes, so a pseudo-Cauchy filter, this is just a filter generated by balls over A. Yes, it's just a chain of balls. Yes, so yeah, so exactly. So it's a chain, it's not a weird thing. Exactly, yes. And so the main thing we want to prove is that this is actually a complete type. And that in fact every type is of this form. Okay, so the main proposition for now is the following. So take A in K of M for A. Let F be the maximal Rideau-Kikuchi filter over A accumulating at A. So this is just fancy words to say it's what is F? F is just the set of all A balls of a, so it's the set of all, it's generated by all balls over A containing little a. Then what? Yeah, it could, yeah, it should be, yeah, it's the locus of A, exactly. Of A. Then eta F A implies the type of A of A. Okay, so in particular, it's a complete type, and it's this complete type. Yeah, but the eta says negations. It says B A is in B if and only if B is in F. Yeah. Okay, so let's prove this. And we're going to see all three kinds of types we looked at so far appear again. So, well, actually, there's four types really, but the first case is silly. So remember, I allow points to be both just for completion. I mean, so that I don't have to distinguish cases. And in particular, what could happen is that little a is in A. Okay, so first case, if F contains a point, a singleton, then it's okay, because this is a realized type, and this already says I'm equal to that point. Contains a point, well, contains a ball, a closed ball of infinite radius, i.e. a point. So a closed ball B. Oh, I forgot ball. So then what you have is that eta F over A implies X is in B, but then it is just B. So it's complete. Okay, so maybe I'm being slightly abusive because the closed ball, it's a singleton, it's not a point. I'm okay, maybe I should write it like this, but which is just a singleton C. Okay, so this is a silly case. The interesting cases start now. So now if F is generated by a closed ball of a non-infinite radius, B of radius gamma strictly smaller than infinite, then we're going to see a residual extension appear. So B, what is it? It's the ball of radius gamma centered at some C, where C is in A. What? What do you mean? It's a filter. So generated by means it's a principal filter generated by a single set. So it's everything. So the F is just the set that contains that given closed ball. Okay. Yes, and gamma also. Gamma is in V because it's a ball over A. Good. So yes. So in particular, gamma is V of some D. And so now if we look at A C over D, the valuation of that is 0. Ah, why? Okay. Yes. It has a center in A and a radius in A, in V of A.
Of something also an A.
Yes.
And that could be an A without the.
A is field generated. A is in the field. I don't know if that's your question. A is not a weird thing with.
But I mean, A's a field.
Yes.
Oh, I see my depth, sorry.
Yeah, so it's not one of these weird substructures where the valuation is not subjective. Yes. Okay. Where was I? Ah, yes. So since F is generated by so the first thing we want to say is that A is not in the open ball centered at C. Okay, because this is an A-ball, and if it were an A-ball, it would be an F. Oh yeah, sorry. All right. This is an A-ball, and if it contained A, it would be an F, but it's strictly smaller than the closed ball, so that one would contradict that the closed ball generates. Okay, so A cannot be in this open ball, so which exactly means that V of A minus C is equal to gamma, which is V of D, which tells us that V of A minus C over D, which was the thing I wrote earlier, is 0. Okay, so that tells us that we can take the residue of A minus C over D, and this is some alpha, and this alpha can't be in if alpha, so alpha, if alpha is in res of A arg, which is equal, remember, A is algebraically closed, we assume that, so the algebraic closure of its residue field is just its residue field. I'm trying to explain what this type looks like. Yes, and it's a residual type. I'm trying to explain that it's essentially a residual extension. Yes, exactly. It's even, yeah, exactly. I'm trying to find a map to the residue field. So this alpha here cannot be in here, because once again, res minus 1 of alpha would be a ball over A. Actually, it's exactly this ball. No, sorry, it's another ball. Res, this would be that would be a ball over A, which is strictly included in the initial closed ball B. So A cannot be in it, but A is in it. Sorry. So what do I mean? This is a contradiction. What?
Are you saying something about that? I mean, why did you mention occupied closure?
Because I want to apply my lemma afterwards. So not only it cannot be in res A, but it cannot be in res A in the algebraic closure because they're the same.
You're not using it yet.
No, I'm using it later.
Yeah. Okay.
Maybe yeah.
Okay.
It's not in the algebraic closure because these two things are equal. That's all I'm saying.
Excuse me.
And yes.
It's not res minus 1 of alpha. It's the preimage after you've applied your your affine transformation, I think.
You're right. Yes, you're right. So you need to, so you take res minus 1 of alpha, and then you recenter at C, and you multiply by D. I think that's it. This is an A-ball, which is strictly contained in B, and it contains A. So we have a contradiction, which is a contradiction. Okay, so So this is not possible. Okay. So alpha is not in res of a. Yeah, so maybe here, this part is not important. It's now that it becomes important. And now we can apply our, so let's call this E. And now we can apply our theorem on residual extensions, because the type of E over A is uniquely determined well, what do I mean by that? But it's uniquely determined by nothing really, by just being yeah, so what do I mean by that? I mean that if we take another, so if we take another E prime, so if we take another A prime realizing eta F over A, then we can define E prime to be A prime minus C over D. And the residual extension lemma exactly says that these two things have the same type over A. E is elementary equivalent over A with E prime. Okay, because they're both lifts of transcendental new residue elements. So the type is unique, and so they have the same type. And if you know that E and E prime are equivalent over A, since C and D are in A, this immediately implies that A and A prime are equivalent over A. Okay. Second case, let's assume that F is not principal. It's not principal. Third. Oh yes, you're right, because this is case 0. But yes, that's third case. No, yeah, you're right. Third case. It's just I forget this case because it's kind of silly. It is an important case. I agree. If F is not principal and there's no accumulation point. So there's no point in A that lives in the intersection. Remember, this thing is just the intersection of all B for B in F. Well, then if we take a polynomial P over A, if P looks like it should have a 0 on F, so if 0 is an accumulation point of the image filter, we showed that so this is the immediate extension lemma. The existence part of it showed that there would be a root of P.
Can you remind what is this?
What?
What is the star F?
Ah, so bar is okay. So P star F. P star F is the filter generated by P of B, by the set of P of B where B is in F. You can check it's a base, it's a filter base. And the accumulation point is and so P star F bar is just the intersection for all B in F of P B, and then I need to take a closure. Although I think this set is closed, so it's okay. But I'll take a closure just to be safe. Actually, I know it's closed, but whatever. Anyway, so we proved that if it looks like P has a 0 on the filter, then it actually has a 0. So this implies that there exists a C in A. Well, there exists a C in M such that P of C equals 0.
Sorry,
Yes.
again. What is the overlying P of B?
The topological closure. And this is closed, so you don't even need it. But I've never proved it's closed. So. But yeah, so the important fact is just that we prove that if it looks like there's a zero, there is a zero. And this looks like a topological fact, but we proved it in a purely algebraic manner. But, yeah, so there is C in F bar, but that implies that C is in A alg, which is just A intersect F bar, which is a contradiction again. P is not zero. Otherwise, this is not very interesting. So this shows that there is no non-zero polynomial that looks like it should have a zero. And so now by the immediate extension lemma, we have a complete type again. So the immediate extension lemma, it tells us that if now we take an A prime that realizes the generic of F over A, we have exactly the same consideration. So there's no P, etc. And so A is equivalent to A prime over A. Because there's a being an accumulation point of a pseudo-Cauchy filter, which does not look like it should have zeros in it, is a complete type. We proved that. Good. So one last case. So the last case is F is not generated by a closed ball and F bar intersect A is non-empty.
When there is some ball over A, contained in some ball over A, not in the filter, but in the section.
We've ruled that out here. Well, we haven't ruled it out here because I mean this could be the case. But so look, my disjunction. But we're in the process of ruling that case out.
This could happen.
This could happen now. Exactly.
But it's not on the two where the case happens, doesn't happen.
Yeah. So essentially, we've shown that in that case it cannot happen because the type is complete. So there's no A ball inside of it. Otherwise, the type wouldn't be complete. So the only case it can happen is now. But yes, we're in the process of describing when this can or cannot happen. But if you look at the disjunction is really on when there's actually points and not when there's balls. But so implicitly, we're showing that if there's a ball, there's a point. Yes, that's actually it is actually an important remark. Yeah, so let's look at this case now. So let's call C this element. Okay, and I want to look at V of A minus C. Okay, so if V of A minus C is in V of A, so is equal to some V of D with D in A. We want a contradiction, so we're going. How do we get it? Well, this is exactly saying that A is in the closed ball of radius V of D around C. So this thing here is in the filter. But the filter is not generated by a closed ball, so we know there's a smaller open ball. In particular, the open ball of radius VD must be in it because it's the maximal open ball inside of this. So this immediately implies that B of VD C is also in F and hence contains A. But this is a contradiction because that implies that V of A minus C is strictly greater than V of D, which was by definition V of A minus C. So this is a contradiction. So we're almost done. Yes, so we know that V of A minus C is not in V of A, which is equal to Q to its divisible whole, because A is algebraically closed. And now we apply the ramified extension lemma. Because we have a new valuation which is not in the divisible whole, and so any lifting of it has the same type. And actually, any lifting of something realizing the same cut has the same type. So let me just call this is E. And if I take A prime realizing eta F over A, the same computation shows that V of A prime minus C. So this we call E. No, there's a little something to prove, sorry. Yes. Yeah, sorry. We need to prove it's the same cut. And it's not hard, but we need to prove it. Because I needed to do something more stronger here, but I forgot. Let me erase here. Oh, let me think what's the most efficient way of doing what I want to do. Actually, let's not think and let's ask my phone. Oh, sorry, where am I? Oh, yes. So pick any. So we just need to do a slightly better version of the argument I just did. Gamma in Q tensor V of A equals V of A. So gamma is equal to some V of D. V of A prime minus C is greater or equal to gamma if and only if. So this is the same as saying that the closed ball containing gamma centered at C is an F. Okay. And yes, which is equivalent to by the exact thing we did over there. So if we have a closed ball, then we also have the open ball. So if and only if of A minus C, strictly A prime. But look, this here does not mention A prime. Okay, so this is also equivalent to V of A minus C greater or equal to gamma, and if and only if V of A minus C strictly greater than F. So they have the same cut. Yeah, because we have this equivalent this. I mean, we have the same cut, and it can't be equal to A. So this part really we already proved. But, so I'm just turning this part we already did. We already took care of. But anyway, what we've proved is that they have the same cut. So if we call that E prime, and if we call that E and E prime have the same cut over Q of A, of the divisible whole of V of A. And so by the ramified extension lemma, E prime is equivalent to A over A to E, which immediately implies that A prime is equivalent over A to E. And this concludes the proof. Because you can check that the 4 cases cover every possible cases. And an important remark is that we've actually related the more topological description in terms of being in chains of balls to the algebraic description in terms of residual, immediate, and ramified extensions.
Can you just summarize? So there's an algebraic case.
Yes.
The second case is when you add
A new residual element.
third case
You don't add anything.
nothing.
Case is you add a value group element.
And so now in the third case, it is the third case has nothing. But over additional parameters, what do you add?
Over additional parameters, you would have a gamma element.
Generic parameters.
Yeah, so immediate extensions are almost orthogonal to gamma, but they're not orthogonal to gamma. If you add a point to, you see, if you add a point to the filter, you get into that case.
So in essence, you only really use the fact that the residual field is quite close.
No, I use that it's algebraically maximal. So I use the fact that the residue field is algebraically closed, the value group is algebraically closed, and it's algebraically maximal, which, as you know, is equivalent to being algebraically closed. But, yes, yeah, because otherwise you could have this could what could happen is you have a yes. Good, and yes, so and we also note Annan's remark, which is that if the accumulation points are F, so if the chain contains an able, then it must contain a point, because we can check all the cases. Okay, so here it does not contain any point, but it does not contain any ball either, because otherwise the type wouldn't be complete. And here it contains a point. Okay. Already? Let me finish one thing. I'll finish one thing and then it's time for a break. I can start erasing this. So we described all types, all one types in the field, but I promised you a description of every definable set. But now it's just it's pure abstract nonsense. I mean, it's compactness. Yes, but we get something better.
Silvain, I don't understand maybe something in the notation. When you say that C is in A and in F bar is just intersection of all balls?
What?
When you say C is intersection of A and F bar.
Yes.
F bar is just the intersection of all balls?
Yes.
So C is the ball that contains.
No, C is a point.
Well, you allow points to be.
No, but this is the intersection. It's the intersection of all balls in F. But so the point. This lives inside K of M. This is a set of field points.
Yes. So C is a point in.
Yes.
And in the field of A.
It's not in the filter because it's not equal to A.
I mean equal.
The F is the filter, is the maximal filter containing A. So a ball is in there if and only if it contains A. The singleton C does not contain A. No, is that your question?
What I'm asking is, doesn't this imply that it's equal to A?
No, because I'm not saying C is in F. I'm saying C is an accumulation point of the filter. I'm saying C is a pseudo limit of the pseudo Cauchy sequence. So yeah, so this is not the intersection of, this is not the set of balls that are contained in the chain. This is the set of points that are contained in the chain. Yes, so I just need a definition. So Swiss cheese is a ball minus a finite set of balls. So is a set B minus union of the BIs, where B and the BIs. So let's say a Swiss cheese over A is a set like this, where B and the BIs are balls over A. And the BIs are strictly included in B. So this is strict. Okay, so good. Did I forget to say finitely many? Yes. So this is a Swiss cheese, and so we say, so this is just terminology, that B is nested, so sorry, B minus union over I of the BI is nested in D minus union over J of the DJs. So, and M if the outer ball of B is an inner ball of D. Okay, so this is like a silly case. It's you have a you have two Swiss cheeses, but in fact the union of them is also a Swiss cheese. So this is the kind of case we don't want to consider. Okay, and the theorem we've essentially just proved, which is U2 wholly, is that every A definable X inside the affine line is uniquely a finite union of non-nested Swiss cheeses.
Well, A again is algebraic.
Over A. Yeah, same A as before. A inside of Km is algebraic. And this is just, this formally follows from what we just proved, because we just proved that, well, there's some work, but it almost, the uniqueness part is does not follow, but the existence part follows from what we just proved, because we just proved that if we look at the set of balls, it completely determines every types. So by compactness, every set is a Boolean combination of balls, and you can check that finite union of Swiss cheeses are closed under Boolean combination. So they're exactly Boolean combinations of balls. And then by what I just noted, if you have a nested case, you can replace it by another Swiss cheese. So you can always assume non-nested. And the uniqueness part is not very hard. This essentially follows from the fact that you can't cover a ball with finitely many balls. So if you have a Swiss cheese inside a union of Swiss cheeses, a finite union of Swiss cheeses, it must be inside one of these Swiss cheeses. So that gives you uniqueness.
An extrapolation, the Q just gives you something involving followed over.
Yes.
And this is very just have a geometric description as no minimality.
Exactly.
RCF is no minimal. You've got to do something.
Yeah. So of course, what you could do also is just take a formula of the form valuation of a polynomial is smaller than valuation of another polynomial, and by hand show that it's a Swiss cheese. It's not very hard either. But since I had all this, since I was going through describing types anyway, I think it's I like doing it this way. Good. So this describes what sets looks like in K, and it's time for a break, I think. Yes.
In the definition of nested, it seems to me now that it just says that B is in some ball rather than.
No, because you could have if you have a Swiss cheese and then you have a smaller Swiss cheese, so this is not a Swiss cheese. It's two Swiss cheeses. It's the union of two Swiss cheeses. Okay, whereas if you have your first Swiss cheese, maybe the drawing is not great, and then you have your second Swiss cheese. This is a Swiss cheese, because you can just forget about this ball, and it's just this ball minus this ball. This is not a Swiss cheese because you have a hole here. So nested is really the outer one is the inner one of another one. If you want the union of two Swiss cheeses to be a Swiss cheese, you really need equality. No? Yeah.
You should have bought a Swiss cheese.
Yeah, but then it's hard to fit a Swiss cheese inside a Swiss cheese.
Just by Jan Horry. But it's actually the paper, right? I mean, this is the main result of the paper.
Yes. Yeah. So the proof goes in the other direction I said, which is that she uses quantifier elimination to show, I mean, to explicitly show everything is a Swiss cheese. So she describes the shape of V of Px smaller than V of Qx. But I mean, it's in the end, that's the theorem. Yes. Yeah, well, A is essentially a model, except that because no, it could be trivially valued. So it's a little bit more general, but it could be trivially valued. So it could not be a model, but then it's not very interesting if it's trivially valued. The interesting case is when it's a model. Yes.
What do you mean by uniquely?
There's a unique decomposition. There's a unique way to write it as non-nested finite union of non-nested Swiss cheese. Oh yeah, you could repeat Swiss cheeses, of course, that wouldn't be unique, but yeah. So without repetition, yes. Essentially, because there's no way to write, if you have a finite union of Swiss cheeses and another finite union of Swiss cheeses, and they're not nested, they're non-nested on the left and non-nested on the right. If they're equal, then there's a one-to-one correspondence between the Swiss cheeses. Because, it's a little, you have to work it out, but. Yeah. And essentially, the key case is if you want to cover a ball with finitely many balls, you can't, unless one of these balls is the ball itself. Then you have to do a convoluted version of that argument because you have to deal with the holes, but it's essentially that argument. Yep. Thanks. I mean, if you have more questions that don't require the board, we can. I hadn't planned. Yeah. So what we've just proved is that ICVF is C-minimal, but I didn't intend. I mean, developing the theory of C-minimality is It's a lot of work if you just want to talk about ACVR.
I've got an idea about this topology, so I'll still understand it.
Yeah.
Explains everything.
And the kids just saw it, probably a hawk, I think. Oh yeah, in the pigeon on the street. Yeah, I think this is a hawk.
I think it's a hawk. For some reason, I've never seen white
But
brown spot.
Hawks do live in cities.
It's in Toronto, maybe.
No, but
in general, yeah.
In general, yeah. So I think there's like 10 of them in Paris or something like that. I mean, there's
10
not-
kinds of 10
no,
actual.
10 actual birds. No, I don't remember the number, but it's extremely low. But
You should at least remember the names, I think. if it's only 10. Probably have names. Full names.
no, maybe I'm joking. Maybe it's a few hundred.
Yeah,
But I think it's not completely. You don't see them a lot because they're nocturnal, mostly. I think. I don't remember. No, they. Well, I don't know. But I think it's not completely uncommon.
yeah. So thinking with the filters is a bit.
Well, I think
No, it makes sense. I understand.
it's not just it makes sense. It diminishes massively the quantity of computations you have to do.
Well, it makes sense when you talk natively. Yeah.
No, even for Henshin, it makes sense.
I can't believe that. What do you mean dimensions? I mean, they're just hidden somewhere. No. I mean,
Yeah, it's just that you stop. You
They're
stop.
hidden in
Because-
a different place. I mean, you can't. Get
No,
around
because
them,
it's just that when you have pseudo-convergent sequences, you do the same computation over and over.
Yeah, because you always have to choose the sequence.
You have to choose a sequence, and then you have to show that. And so you do it all the time over and over, and now I do it only once, and
Okay.
and then it's purely more. I mean, it's just that it contains all the information that you want to compute. In my notes, yeah. But in fact, it's how it's done in topologie générale.
Okay.
In Bourbaki.
Yeah.
So that they have premises of Kaplansky theory there.
Ah.
And they
I
do
know-
it with
never
they do
saw
it
that.
with filters. So yeah, it's Bourbaki, which should be expected since it's filters. So, oh, Françoise, maybe let's wait for Françoise. And let's also wait for the bolts to dry. Are there questions before we start again? From the chat or from you? All right, maybe we should start. Hopefully François will come along. Yes, so now what I've done for now is describe what sets in the field itself, well, in the field itself in dimension 1 look like. So what I want to do now is explain what they look like in the residue field and the value group. Okay, so definable sets. And it's in a way it's easier. It's just that I need a little terminology to explain what I mean by everything. So let's define a few things. So let K be an empty set definable set, and we say that D is stably embedded if for all, so D is in some theory T, in some M, in some structure M. If for every M definable X inside of some power of D, X is in fact D of M definable. Okay, so why is it called stably embedded? It's called stably embedded because in a stable theory, every set is stably embedded. Well, so the stably here comes from the fact that my guess is it comes from the fact that it's the behavior in a stable theory. Then we can.
It means that all types are
Yes, but it's yeah, exactly. Okay. Now, if D prime is some L prime structure interpretable, well, empty set interpretable, let's say. In M, we say that it is pure. So interpretable in M on some set D. We say that it is pure if every on some set D which is stably embedded. Yes, it's the domain. It's the domain of interpretation. Yeah, it could be imaginary. I don't care. Well, so you have an interpretation. So you have a domain of interpretation of the interpretation. So maybe this is not. I mean, I just want to. So here we just say a set is stably embedded, but now I want to say a structure is stably embedded with and explain what the structure is on it. But so I take a structure, I interpret it in M, and I say it's pure if all the structure on it is given by L prime. L prime. Actually, okay, we don't need stably embedded for that. So if every definable, yes. Yeah, but so we're just specifying what the induced structure is. Yes. If every definable set X inside of, so zero definable set inside of dx to d to the n is in fact L prime definable. Okay. And last bit of terminology, D1 and D2, two zero definable sets are orthogonal if the only definable sets you can define inside of them are, so here are, I mean, really what I should probably call that is almost orthogonal over the empty set, but if we are being very, very precise, if any X inside of D1 cross D2 some n some m zero definable is of the most basic form possible. So inside of here, we obviously have the thing that we must have are finite well, the things that we must have is products of definable sets from here, and then finite union of these. And we say that they're orthogonal if that's all we get. If every zero definable set is a finite union of xi of x cross y with x inside of d1n and y inside of d2m, both are empty set definable. Okay.
You cannot use X again.
Ah, yes. And yeah, so I mean, maybe in the case of ACVF, the quantifier elimination gives us a very precise statement. So maybe we don't need the terminology, but the terminology exists and is used all over the place. So I thought it would be interesting to at least give it. So let's take M, a model of ACVF. So now it's a structure. It might have K points and gamma points, and so it's an actual structure. So the proposition is the following. So if X inside of K to the N is A definable, then X is ring of, actually, maybe let me write the complete, let me write only one proposition. So let's take the most complicated case. Let's take something that lives in K cross gamma, is A definable. Then X is a finite union of Z Y cross Z with Y inside of Kn is ring A definable, ring K of A definable, and Z inside gamma of M is ring, what is ordered group gamma of A. Okay, so this is a very precise statement. In other words, although it's more precise, so in part, so I should really say in particular, and this is just rephrasing, K and gamma are stably embedded pure, so respectively ring or ordered group stably embedded pure and orthogonal.
Why don't you say in part two about just call D1, D2 fully orthogonal? You know.
Yes, yeah. So I could have defined that also, but yes, right. Maybe that would have been a nicer thing to define. I could have defined fully orthogonal if for every M definable. Yeah, maybe that's a better definition to give. It's a more reasonable definition. You're right. Well, I mean, I don't think you need it.
But here you didn't take.
But anyway, the thing is that when they're stably embedded, you only need to look at the zero definable structure anyway. But
In the proposition, though, you didn't take the model, right?
nope.
I mean, if you find it to be orthogonal. I mean, if you define orthogonal to be.
Yeah, but it's a particular case. Take M A equals M. But you say more because you also know that that the different parts are actually ring definable over the residue field and ordered group definable over the value group. So you're saying more.
You're trying to three propositions in one proposition.
Exactly.
Yes, very good.
To be exactly exact, yes. And the proof is very easy. It's an immediate consequence of quantifier elimination, because you can check these things. These things are so finite unions of products like this are closed under Boolean combination. So it suffices to check that atomic formulas are of this form by QE. It suffices to check that atomic formulas are of this form. But there aren't that many atomic formulas. So there's essentially two atomic formulas. Well, there's three atomic formulas, but so I erased my language. But essentially, what formulas can we have? We have V of P. So how do I want to write it? So what's an atomic formula? So essentially, the only thing you can use to define atomic formulas is equality on the field, equality on the value group, and equality on the residue field. So you have V of P of A. Sorry. So what do you have? You have a certain term in. So how do I want to write this? So it's really easy to see, but it's a little annoying to write, like most syntactic things. So first, maybe we should rule out. Yeah. So if the atomic formula is defined by equality of two polynomials, if it's well, so sorry. The thing is that remember the set is inside K and gamma, so the free variables are inside K and gamma. And so if you have an equality on the valued field itself, it can't have free variables because there's no way. I mean, they can't appear because you can't use gamma and K variables in a polynomial equality. So X cannot be defined by equality of polynomials. But so it could be defined is equality of certain things. So what you could have is you have a bunch of variables from gamma, and then sorry, and V of certain polynomials applied at A and stuff like that equals some other term like this. Okay, but this is in V. This is clearly in gamma A. And you could also have constants. I mean, I haven't written everything, so probably I should write it like this. This is a constant from gamma A. And so you can see this is indeed a formula. It's an L-ordered group formula in parameters gamma A. This is the only thing that can appear. And you don't, and in that case, Y is everything, because the variable in K do not appear. And similarly, on the other side, you could have X and R of PA QA, and then some alpha, and then more stuff equals to S of exactly the same things. And this, once again, is in K of A. This is in K of A. Maybe I should have called them X and so yeah. So maybe I should have called this Z and this I should have called Y to be consistent with my Y and Z here. Anyway, and you can also check that this is the only formula you can possibly write with equality in the residue field, and you can check that it is indeed a ring formula with parameters in Ka. It's just there's nothing else that can happen because you don't have any other functions. So this is not very But this is still extremely important because it says that in ACVF you have a pure algebraically closed field that lives around. You have a pure DOAG that lives around, and then there's a whole theory built around how does the whole structure is controlled by these two things, and you have domination type results that I'm not going to get into, but there's the presence of this strongly minimal set and this O-minimal set in ACVF is the basis for a lot of the theory of ACVF, which I'm not going to get into. Yes. So one last thing I wanted to do is describe the algebraic closure and the definable closure, and I still have a little time. Yes.
Sorry, how does this formula discussion prove that it is a product?
What?
You have an X is a finite union of products. So how do I see that?
Because in that case, yeah. So maybe I should be more explicit, but you get trivial products because here what you get is something of the form k to, so the variables in k don't appear, so you get k to the m cross some y, which is defined by this formula, and in this case you get some z. You get y defined by this formula cross gamma to the m because the gamma variables don't appear. So you get non-trivial products when you start taking intersections.
You could also like just like type over a model of some tuple in little k and a tuple in gamma. To show that type determined by what happened on each side separately, and then by compactness you get compactness gives you the definable section.
Yeah, so this is a little finer than working over a model because here I'm working over any substructure, but yes, but you could also do the compactness argument over a substructure, is what I mean. And it's a little more precise, and you do get things out of it from the more precise things, but yes, so let's finish by describing the algebraic closure. I wanted to have, I was hoping I'd have time to say something about the definable closure, but it's more complicated. So we'll see if we have time to say something about it. So we can completely describe the algebraic closure. So you take M, a model of ACVF, and you take A, a subset of M, a subset actually. So in all three sorts, then ACL of A. So what is it? In the K sort, it's, so you take KA, and you take the algebraic closure, where once again, I'm being very abusive with this notation. So you first generate a field and then you take the algebraic closure. Union. In the residue field, you do the same thing. And in the value group, you take the divisible whole. So once again, here with the unsaid abusive notation that you first generate a group and then you take the divisible whole. Yes, it's still not a field if I start with the first substructure. So these two are still kind of. Yeah, if I assume A definably closed, then this is also true. But the definable closure is bigger than what you expect anyway. So I don't want to talk about the definable closure. What? Yes.
And then you have to look at, and then gamma A means.
Oh, you're right. You're right. Let's take a substructure. I agree. Let's take a substructure. Because I need to take V. Yeah, you're right. You're right. Sorry, you're right. I need a substructure. Yes. So the proof of that is not too hard. There's one tricky part to it, which we'll get to. The tricky part being that at some point we have to show that we can't algebraize anything in the field sort over these two sorts. But anyway, so let's start. So first, let's look at what's the algebraic closure in the field sort. So let's take let's take the k point of A and look at the field point that we get. That I claim is exactly is Ka, and this is just by the description of types. Okay, because oh, okay, maybe. So this is just by the description of one types. Okay, because remember there were 4 kinds of one types, the realized ones, which are obviously in there, and then over Ka alg. The other, you can check the other 3 are not algebraic because they have, it's easy to check they have infinitely many realizations because they're generic of chains of balls and balls are infinite. So there's no way these are finite. So this is just the description of one types. You can compute the ACL of gamma A inside gamma. And this now essentially follows from what's here, because you have gamma points, and you know it's a pure divisible order abelian group. So what you're going to define is just the algebraic closure in an order abelian group, which is just the divisible whole. And similarly, ACL of K of A intersect with little k. You're in a pure algebraically closed field, so your ACL is going to be the algebraic closure. Okay, so these are the easy parts, but this is not, the proof is not finished because it could happen that there's points in. Actually, I didn't even need gamma here. Sorry. Because here we showed that formula anyway factorized through K of A. So I didn't need, so yes, so the only tricky part left is what can I define over these things that is algebraic in K? And so that's the claim I want to prove now. The tricky, well, the one thing left to prove is if I take ACL of A and intersect it with K. So if I add, if I don't just look at what's coming from the field sort, but the other sorts, do I get any new things? Okay, and the answer is no, but we have to prove it. So essentially, we're proving that we don't have sections.
Is this your statement? Is that part of your statement already?
Yes, but that's the last thing we need to prove the proposition, is that there's nothing coming from these two things in the field sort. So the claim is the following. So let's take alpha in K of M, and let's look at ACL of K of A alpha. So that you have the same proof for gamma, but I'm going to do it for little k. This is included in K of A alpha. This is the last thing we have to prove. Well, and the symmetric version for gamma, of course. And so there's a number of ways of seeing this. My favorite way of seeing it is the following. So, how do we do this? Yeah, so let's assume that this is not in res of Ka alg. I mean what? Yeah, I mean, it doesn't matter at this point. I mean, what I really care about is K of A, but anything in K of M does not matter really. So the first thing is that if alpha is a nice point, so if it's in the residue of Ka alge, then there's essentially nothing to do because ACL of Ka alpha is included in AC. Oh, so the intersection with K, sorry. The K points of this. K intersect is K intersect the ACL of Ka alge, and we just proved that well, this is Ka alge. Yeah, because this is all field points. Okay, so the interesting case is if alpha is not in res of Ka alge, then let's see. Be a lifting of alpha. We've shown that any lifting of alpha has to be transcendental. Okay, so the transcendence degree of C over Ka is 1. Yeah, because if we lift a transcendental residue element, it can only be transcendental. And so now we're going to apply the exchange. Okay, because alpha is in ACL of Ka C. It's even in DCL, but we don't really care. And by what we already computed, this is in Ka C alge. Because these are all field points. Okay, so why am I getting confused now? Now I just want to apply the exchange for, I mean, the exchange property for, I mean, why am I getting confused? This is easy. Ah, yes, because sorry, I did something completely silly. I forgot to what I was trying to prove. I'm trying to characterize this thing. Okay, let's call it C.
Maybe not.
Yeah. E. Yes. In my notes, it's big C, which is easily differentiable from a small c. But yeah, sorry, that's not what I wanted to do. So what I wanted to do is that we can find a C which is transcendental over C. Okay, that's not hard because this is infinite. So by compactness, we can always do that. Wait, and now we can do the computation I wanted to do. So the transcendence degree of Ka C over Ka, this is 1. And it's equal to the transcendence degree of BC over Ka, which is also 1. because I took it. Sorry, I forgot. It's called B now. I took it transcendental over B. So I mean, this is one and this is one because it's a smaller, it's a subfield. So BC over B actually. What? It's BC over B, I think. I mean. No. What is B? Yes, it's BC over B. And now I have a tower, I have KA, B, BC. So why did I pretend? Yeah, sorry. I really mean KA here. So why is this? Because ACL of, well, essentially because B is included in ACL of KAC by construction, which is KA alg. KAC alg, sorry. Yeah, so all the new points here are actually algebraic over C. So the transcendence degree doesn't go up. This is what I wanted from the beginning. And so this tells me that this is the transcendence degree of C over KA. So now I just applied additivity of transcendence degree. So this is the transcendence degree of B over KA plus the transcendence degree of C over B. This is 1. So this is 0. Sorry, this was a bit. Essentially, I'm just using the exchange property for ACL in ACF. This is, I mean, or strong minimality or whatever you want to call it. So I lift the most generically possible. I know that this only gives me new algebraic points. And since I've already added one transcendental element, there can't be any transcendental element here. Okay, and so same claim and with the same proof. If gamma is in gamma of M, then K intersects ACL of KA gamma is included in KL. And now you do an induction and you get the proposition. Okay, because here I've added one of them, but then you can add another one and another one and another one, and you're going to get the same result. Okay, so the proposition follows by induction. Oh, I'm on the back one. I shouldn't have done that. So I just want to point out, and I don't know if, yeah, so it's the end. So I just want to point out, in fact, we've proved, it's a little hidden, but we've proved something very strong. Because we've proved the following. If we have f from gamma n cross km to k, which is definable with parameters, then it has finite image. Okay, so here essentially we've proved the case where we have a function just from k, here a function just from gamma, but it's the same. So yeah, so this is just its compactness because you end up in a set that does not depend on alpha, so you can only have finite image by compactness. Okay, if you have f from k into big K, a definable, and you have alpha in Km, then f alpha is an ACL of A alpha, which we just proved. So let's actually take it Ka definable. We just proved this is in Ka alpha, which does not depend on alpha. So by compactness, f of k is finite. Same proof if you start in gamma, and in fact, here I did it just for one because it's the case we looked the most at. But if you use that statement, you see that the ACL, the k part of the ACL doesn't depend on this and that. So you could add as many parameters here and here as you want. So really, the corollary is exactly the same statement as these two claims. But, I think the claims seemed pretty innocent, whereas the corollary, I think, was what?
Are you sure this proof is like the coded proof there?
Yes.
The proof has to involve exactly this fact.
No, I'm proving this fact.
No, but the proof, the claim has to somehow contain this thing.
Yes.
You want to show there's nothing in K algebraic over little alpha.
Yes, but that's what I've proved.
How?
I've proved that because I've lifted alpha transcendentally, and then this shows that there can't be any transcendental element here, because otherwise I'd have too much transcendence degree.
And why is BC over KA one?
Ah, because of this. Because B is inside KAC alg.
And why isn't algebraic over KAC?
Why B is in there?
Yeah.
Ah, because B is in the algebraic closure of Ka and alpha is the residue of C. No, yeah, but being carefully so. No, so maybe I can redo that properly. So B, I agree. I mean, it seems a bit magical, but I mean, if you want, I can give you another proof, but it only works. It only works in ACVF. I like this proof because it essentially works in any valued field. But so what is B? B is K of ACL of K alpha. Yes. So this is ACL in the sense of ACVF. Okay. Res of C is alpha. Okay, so this here is included in K intersect ACL of KAC, because alpha is definable over C.
And that's K alpha of KAC in the sense of ACVF.
Still, yes.
Okay.
But now this is all field points.
Pardon?
This is all field points. This is field, this is field. And so we showed that the ACVF algebraic closure of field points in the field sort is the algebraic closure.
We have to prove that.
But we proved it. It's the first bullet point we proved. Well, we proved. I said it follows immediately from the descriptions of one times. And so this is inside KAC alg, the field theoretic algebraic closure, which means that this transcendence degree is also 1, because we're only adding elements that are algebraic over Ka and C.
Well, typically KA is not substructure, so you might be taking DCL or something.
What? Yeah, here I'm taking the field closure.
No, I'm saying in one we proved it for substructure.
Yeah, but that's a substructure. This thing here is a substructure.
So you did. You didn't need to
I just need the ring. I took the field, but I really just need the ring. No, I don't need DCL close.
Yeah.
So there's nothing about DCL on this board, wherever, which is good news because DCL is nasty. I mean, it's not nasty, but.
That's correct. Okay. So just the one type business about how the closure of KA is.
Yes.
And the one touch define over the field.
Yes.
Over is a algebraic closure of the field.
Yep. Yeah, so I'm sorry. This might be the most technical thing I did, and I screwed it up because I forgot I did it in completely the wrong way. But so another argument, if you want, but this requires knowing how to build ACVF models of ACVF, is that you can build models of ACVF where these are countable, but the field is uncountable. And in fact, any infinite definable subset of the field is uncountable because it contains a ball and all balls are uncountable. And this also immediately shows that you can't have functions like that because you can't have a function sending a countable set to an uncountable set.
So, what? The other way around?
No. But it's subjective on an uncountable set.
Oh, but okay, but you didn't say it was subjective.
No, but it's subjective on its image, always. And its image is uncountable because it contains a ball. Yes. Yeah, so one last remark. Because I'm not going to talk about DCL, but DCL, even in the field sort, DCL of K of A is not the field is not even the perfect whole of the field generated by A. So it's not the DCL in ACF. This is not true. It's bigger. And that was my plan, but to talk about it. But essentially, what it is, it's the Hansil enclosure. It's the separable part of the Hansil enclosure. So it's what?
In general.
Yeah, it's exactly this. Ah, yeah, okay. It might be equal, but in general, yeah, okay, you see what I mean.
I don't think you mean exactly that.
Don't I mean that?
No, it's the DCL intersected with the separable part that is equal to the Hansil enclosure.
Oh, yeah, you're right. It's the other way around. You're right. So, yeah, it's DCL of KA intersected with KAS, which is exactly the Hansil enclosure. And so if you don't know what a Hansil enclosure is, well, now you have a definition of it. And this is, you can redo everything backwards from there. Okay. So next time, my hope, well, my plan next time is to talk about imaginaries. No, I mean, it's the perfect whole of the Hansil enclosure.
When you intersect in the field.
In the field sort, yes. It's the perfect whole of the Hansil enclosure. Yes. Because I mean, if it's DCL closed, it needs to be perfect. And Hansian field might not be perfect. But anyway. So yes, it's as always, perfection creates issues in characteristic P, but other than that, morally, the Hansian enclosure is the definable closure. So once again, if you want to, I was planning on explaining stuff about Hanselianity out of this fact, and it's done in my notes if you want to look at it. But I'm not going to do it. And next time we'll talk about imaginaries.